when we understand the seismic wave propagation in soil or rocks in medium, so this is the boundaries. So what is the technique? The refraction technique is talking about the refracted wave, which is along these boundaries. So look on that video. What happens if we have this is seismic source? We can use hammer, or sometimes they use explosive. If we have we want to have a very deep information, very good data, so you have you should have a very good source of seismic, which is explosion. But in terms of cost, is explosive, yeah, quite expensive. Then normally we use hammer, but we have to stack a few times to get the very good data. So look on that, we have this is sensor. This is sensor, for example, I say 30, 40. This is 30 from this source. Let's see here is 0. So our distance from the source is 30, and then 40, 50, 60. And then this is first short point, and then they have to move here, and then maybe they can move here and move here, and then up to somewhere here. So they have a few points to get the a few data. Then they combine it, and then they can able to derive the tomography of the ground, I mean the imaging the subsurface in 2-dimensionals way. So look on this video. Blue wave is the direct wave. Look on this. So many that's here we have first blue is direct wave, represent wave travel on the first layer, and then this one another second wave, which is here, which is travel on the second layer, on the top of the second layer, present this line. So here, based on this, we know this is, we have 2 layer cases, which is layer 1 and layer 2. Okay, why we can observe at the 80 meter here for second layer, because this layer at second layer the speed is more than layer 1. That's why this wave can overcome layer first layer velocity of the direct wave. Okay, because this is the speed is faster than first one, direct wave. So based on that, we can calculate the velocity, since we have the distance. When we have distance is meter, and then we can get time of arrivals, so in milliseconds. So we can get the velocity, velocity of this material, and that first layer or in second layer. And this is second layer. They calculate about 250 and 800 meter per second. 2050 meter per second. So for the second layer is faster than first layer. Based on that, they can calculate the h, is the depth of the first layer. So based on that formula, D equal to divided by 2 time power of V minus V1 plus V2 plus V1. Okay, you can calculate that, and then you can get the depth of that rocks, where the depth of first layer to the rocks, to the second layer here. So if you use the software, then you did a few short point, and then you can get the tomography, you call it topography of the soil velocity across your testing point. For example, here we have 110 meters, which is from geophone 1 to geophone 25. This study is 24, sorry, 24. They have 34 geophone at 5 meter spacing. Based on that study, they can able to show the contour of the profile, soil profile. So, for example, here is less than 500 is for this purples. Then you have around, let's say, up to 3000. 3000 is blue. Blue is somewhere here. So this one 2005. So here you can see how the variation of the soil profile here, and here is different, because we get every every point we can get the soil profile. We call that a soil model. Based on that velocity, we can check here. Normally we have the velocity value. This is in meter per second. Okay. For rocks, normally we have most of hard rock is above 2500, 400. If soft rock is about 1000 to 2000, 2100. If we have let's say granite is unwet, which is more higher, 3000 to 6000 meter per second. Frozen soil is normally higher. Okay, for limestone, okay, 2004. But most of unconsolidated material below 900, it's about 900. Below unconsolidated material means sand, clay, silt, which is not rock salt. Soil, normal hard pack about that 2200, 600. Water is 1005. That is another thing that you have to think. So it means that looks like water is harder than soil. It's not like that. It's not. And this is for P wave is like that. This is VP, compressive wave. And then just do sand, thousands, hard clay about that. 600, 200. So based on that, if you have, in this case, if your ground is saturated, let's say you do this test study in our groundwater table is very shallow, 1 meter like our UTHM. So mean that the velocity here must be around 1000, because the velocity is a combination of soil, unconcentrated material, and the water. Water is 1005. So your soil, let's say your soil, for example, soil is 250. Yeah, so the average is about 1000 to 1100. So meaning that's if you're working in the area where the groundwater table is shallow, careful for your interpretation. Yeah, careful interpretation. Not follow to this, but look on this area. Okay, this is for unconsolidated material where is our groundwater table is very high. In higher is very deep, So this area is normally is not saturated. It's unsaturated cases. Okay. So this technique is normally can use to determine repeatability of the material. So based on that, you can use this is based on D8 Reaper performance. You can check in your Google's what D8R looks like. Reaper is a huge machine to read the rocks for us works. Okay, so if the velocity is normally less than 1008, 1008 here, normally that soil can be reapable. If beyond that is marginal, and if more than that is not recoverable. Mean if not recoverable, you have to do blasting. Use explosive to as a method for the earthwork. Okay. Then, for example, here if you have granite is 1007, 1008 is considered as recoverable. Then, if more than nearly 2000 is marginal, is recoverable. Then 2000 is considered as non-recoverable. Means you have to use explosive in your method for your excavation. So we have another table for D9. Okay, so you can look on that table. This is for excavation based on seismic and type of material rocks. So